right, good morning. Thank you so much for coming. I'm here to share the latest discovery from NASA's Kepler mission. And this is a result that is the effort of so many individuals. I think this paper has something like 54 authors on it. It's a tremendous result. A lot of expertise has converged on this one result, and I just am the one that has the lucky privilege of being up here to share it with you. But I'd like to start by reminding you of what Kepler is. This is NASA's Kepler mission. Its objective is to determine the frequency of Earth-sized and larger planets in the habitable zone of stars like our Sun. More simply put, though, the mission is tasked with finding out if Earth-sized planets in our galaxy are abundant, paying special attention to those that are potentially habitable. How we're doing that is with transit photometry. So Kepler identifies planets by measuring the brightnesses of stars, many stars, thousands of stars, very, very precisely. Searching for the very tiny dimmings of light that occur when a planet passes directly between the telescope and the star itself, thereby blocking out some of the light. Kepler takes one measurement every 30 minutes of 150,000 stars simultaneously, and does so for a period of 3.5 years, looking for these dimmings. Here in this animation, in the cartoon on the bottom, we've got a measurement of brightness as a function of time, and that dip is representative of a transit event where you've got this dimming, and we call this a light curve. An Earth passing in front of a star like our Sun would cause a change of brightness of only 1 part per 10,000. You've got 10,000 light bulbs and you take just one away. That's the brightness change that we're trying to measure. And we've done something very close to that. We've detected a brightness change in the light curve of a star that is merely 1.5 parts per 10,000. So I'm here today to announce the discovery of Kepler's first rocky planet, Kepler 10b. Here she is, rendered artistically. We do not have a picture of her. This is our artist's rendition, and I'll come back to our artist's depiction in a second. But what I'd like to do is really share with you the story of her discovery, and more importantly, how we know, without question, that this is a rocky world. Kepler 10b orbits one of the 150,000 stars that the spacecraft is monitoring between the constellation of Cygnus and Lyra. We aim our mosaic of 42 detectors right there under the wing of the Swan, just above the plane of the Milky Way galaxy. The star itself is very similar to our Sun in temperature, mass, and size, but it's older, with an age of more than 8 billion years compared to the 4.5 billion years of our own Sun. It's a quiet star, slowly spinning with a weak magnetic field and few of the sunspots that characterize our own Sun. It's 560 light years away from our solar system and one of the brighter stars that Kepler's monitoring. 560 light years. You subtract that from 2010, you get something like, 1450? And I Googled 1450. It's a super stupid thing to do, I suppose, but I Googled it, 1450. And you get a Wikipedia site, which is the age of discovery. So when the photons were leaving this star, Europeans were crossing the Atlantic for the very first time. And here we are, we're still exploring, right? Yet our crow's nest is a spacecraft called Kepler. It's a little bit different. All right, let me show you the discovery data itself. This is our Kepler 10 light curve. This is actual data. Every point you see on this plot is a brightness measurement as a function of time. There are some gaps in this. Sometimes the spacecraft has to stop taking data. For example, when the spacecraft rolls to keep the sun sensors pointed at the sun. So there are some gaps. But perhaps your eye can already pick out some transit events in that light curve, some brief dimmings of light. And I'll mark them for you here with some red vertical lines. I'm sorry, they're not red, are they? They're blue. Some blue vertical lines. So let me toggle that back and forth. There they are. There are the transits. But that's not the transit I'm here to tell you about today. This is a 45-day transit event, indicative of an object that might be a little over 2 Earth radii, and we don't actually see this yet in our Doppler data. But what I do want you to focus on is the data underneath this green band. And I'm going to zoom into that. I'm going to expand it so you can see the brightness measurements laid out more carefully. And here's what they look like. We've got one blue vertical line remaining. That's that other transit event that I told you about. And perhaps your eye can now pick out the other transit event occurring at a much higher cadence and is much shallower. And here, now I'll mark those with a red vertical line. There we are. There they are. Those are our transits of Kepler 10b. So Kepler 10b, unlike this other outer transit event, has a periodicity of 0.84 days. It orbits its parent star once every 0.84 days, less than 1 day to orbit its star once. If I take all of those individual transits and I chop them up and I stack them one on top of the other, we call that a phase-folded light curve, and that's what's depicted on the right-hand side of this animation, the phase-folded light curve, where now you can see the transit quite clearly. We can average all of those points together and get very, very high precision. The transit itself gives us information about the planet radius, right? How big the planet is dictates how much light is occulted, how much dimming you get. However, that's relative to the size of the star itself, right? A Jupiter-sized planet, after all, orbiting a giant star is going to give a very tiny dimming of light as well. So in order to derive the size of the planet, you need to know the size of the star itself. And we had a rough estimate of what that might be before we even launched, actually. We took some measurements and we knew about what it would be. We knew that this candidate, if it turned out to be a bona fide planet, was going to be about 1.4 Earth radii. Right? But there are astrophysical signals in nature that can masquerade as a planet transit. So we're not done. We don't have a bona fide planet yet at this point. We have to confirm it. And we did that with Doppler measurements. And I will mention that this transit event that I'm showing you was the first transit event of a potential planet that could possibly be rocky or that's in that super-Earth regime ever that Kepler found. This was identified in our commissioning data, and it was presented at a meeting in July of 2009, just a couple months after we started taking science data. And so by August, we had already confirmed that the star was, pretty much what we thought it was, kind of a G-type star, typical G-type star. And we started taking those Keck observations, high-precision Doppler measurements in August. We took our very first one. And we got 17 high-precision Doppler measurements in August. And it was a beautiful thing to watch, because as each measurement came in, where the velocities were supposed to be high, they were high. Where they were supposed to be low, they were low. The puzzle pieces were fitting together. But by the end of that observing season, we couldn't pin down a mass necessarily. The signal was just beginning to emerge from the data, but we could constrain it. We knew it was going to be something, less than 6.5 Earth masses or so. But we decided to wait and to take more data, and we did so the following year. We got another 23 observations in 2010 with a Keck 10-meter telescope. And on the right, we've got a plot of the actual phase-folded measurements. The 40 measurements have been averaged together to tease that signal right out of the data. And you can see that it beautifully fits a Keplerian model that is constrained by the transit photometry. I mean, where we expected those velocities to be high, they were high, and where we expected them to be low, they were low. And these Doppler measurements give a mass of 4.6 Earth masses. Now again, even the Doppler measurements, though, are relative to the size of the star, to the mass of the star, I should say, right? Doppler is detecting this wobble as the parent star and the planet both orbit about their common center of mass, right? And how much that wobble is going to depend on the gravitational force between those two objects, right? So it depends not only on the mass of the planet, it depends on the mass of the star itself. These measurements are relative to the star. You have to know something about the star. And so what makes this result that I'm sharing with you so important and so unique is that we know the properties of this star with an accuracy of something like 2 to 6%. And this is why. The star, as I said, is one of the brighter stars that we're observing. It's about 11th magnitude. And we knew that we had a chance of seeing very high frequency variations in its brightness output due to oscillations on the star itself, due to star quakes. We knew we had a hope of seeing them. And so in September of 2009, we started observing this target not at a 30-minute cadence, but at a 1-minute cadence, so that we could try to see those high-frequency variations. And that study is called astroseismology. And the idea is very simple. In the same way that we use a sonogram to probe the unborn fetus, in the same way that we use earthquakes to probe the interior of the Earth, we use starquakes to probe the interior structure and properties of the star itself. And in this cartoon, I've got a Doppler sonogram there. The green curve is meant to represent the high frequency variations that you might observe. This is not noise. These are actual brightness variations that we measure. A tiny star would yield different frequencies than a large star, just as if you strum a violin, you're going to get a very different sound than if you strum a cello, for example. You're going to get a deeper sound. And so by measuring the frequency of these brightness variations, we're able to ascertain the radius, the mass, the age, and the radius and mass specifically to a precision of 2 to 6%. And so we know what this star is. This is a G4 star at the end of its main sequence lifetime. It has a mass slightly less than that of the Sun, 0.9 times the mass of the Sun, a radius of 1.06 times the radius of the Sun. It's older, as I said, more than 8 billion years as compared to our Sun, 560 light years away. So all of our very best capabilities have converged on this one result. Our high precision transit photometry, our very high precision Doppler measurements, and this astroseismology result make this very unique. And they all converge to form a picture of this planet. We've got our transit light curve, which gives us radius. Once we know these stellar properties, our Doppler measurements give us mass, and together, mass divided by volume is density. And we know that the density of this object is 8.8 grams per cubic centimeter. All right, well, what does that mean? What is 8.8? Well, when we talk about planets in our solar system, or let's focus on terrestrial planets, the inner planets, we're used to thinking of densities of like 5, right? 5 grams per cubic centimeter, not 8. So let's put this into context. How do we go from that number to understanding what its composition really is? So here in this diagram, this is a plot of radius on the y-axis and mass of the planet on the x-axis. And we've got various lines that are being traced out, right? So you take a bunch of material, you've got water, you've got ices, you've got silicates, you've got iron, and you put them together in certain mixtures, certain fractions. And you put a certain amount of it, a certain mass, and you ask yourself, what radius do I get? What density do I get? And you trace out these lines. So for example, the line in the middle marked Earth composition. That's the recipe for making those types of planets is a mixture of ingredients very similar to the composition of our own Earth. And you put them together in different quantities, you build up the mass, and any planet that has an Earth composition, that mass fraction of those elements is going to lie on that line according to our theoretical models. And indeed, Mars, Earth, Venus, they do. They pretty much lie on that line. And Kepler 10b is there represented as a red ellipse. And the size of the ellipse is meant to represent the uncertainties in our measurements. And there is no other theoretical model that passes within that error ellipse that is not consistent with a rocky world. There are 2 other known exoplanets there that are shown for comparison. We've got Kepler 10b, which hovers just above Kepler 10b. It's very similar. It has a very similar period, 0.8 days, but you can see that the error bars are quite large. Kepler 10b is a very tricky star because it's very magnetically active, and that leads to these very large error bars that capture not only the rocky planet theoretical models, but models of different composition. And then Gliese 1214, the other of the very small exoplanets, transiting exoplanets discovered to date, is up there near the model for the gas envelope ice giant. So it's by comparing to these theoretical models that we know what the composition of Kepler 10b is. Okay, what I'd like to do now is go back to our ARTIS rendering. As I said, 560 years ago, the Europeans crossed the Atlantic for the first time looking for new horizons. Perhaps one day the ocean we cross will be the galaxy itself, but for now, we're stuck with imagining, right? So we take all of this information that we have, all of the knowledge that we've accumulated, and we put it in the fingers of the artists, and we let them make this world come alive, and so that's what I'm going to show you right now. Kepler 10b is this tiny little speck to the left, barely visible there. Here she comes, orbiting more than 20 times closer to its star than Mercury is to our sun. As such, she's a scorched world with a dayside temperature in excess of 2,500 degrees Fahrenheit, very close to the temperature of melting iron, far in excess of temperature of typical lava flows on Earth. We suspect that the intense radiation from the star prevents it from holding on to an atmosphere, but here we see flecks of silicates and iron, particles that boiled off a molten surface and got swept away by the stellar radiation, very much like a comet's tail gets swept away from the sun when it comes in its close approach. As we fly over the surface here, we're gonna give more liberty to our imagination. The surface gravity is more than twice that of Earth, so we don't expect this planet to have built up big mountains. However, we do imagine maybe that there are canyons, not carved by water, but perhaps carved by lava flows. The night side of the planet is expected to be hundreds of degrees cooler than the day side, so on that day side where we expect to find oceans of molten material. Many years ago, before Kepler, our team built a robotic telescope up at Lick Observatory to learn to do transit photometry. And we called that robotic observatory Vulcan. It was the Vulcan telescope. Named after the hypothetical planet that scientists in the 1800s thought might exist between Mercury and the Sun, the one that was supposed to explain the anomalies in Mercury's orbit. Those anomalies, of course, ended up to be explained by general relativity. Vulcan is the god of fire in Roman mythology, which is, of course, a name befitting of a world so close to its star. And I just wanted to share with you, this feeling that I had when the artists made this come alive for me. It was a very powerful moment for me, having worked on this Vulcan telescope for so long. When I saw the artist rendering of Kepler 10b for the first time, the thought that immediately came to my mind was, wow, this is our planet Vulcan. Here we've come full circle. In our quest for these planets. So let me just summarize our two kind of take-home messages here. First of all, Kepler 10b is orbiting a star very much like our own sun, but with an age larger than 8 billion years and at a distance of 560 light years. And we know that this is one of the best known stars harboring an exoplanet that exists to date. Kepler 10b itself is the smallest exoplanet discovered to date and the first unquestionably rocky planet orbiting a star outside our solar system. It's an important milestone for our team. I personally think it's an important milestone for humanity, and I just thank you for being here to share it with us.